from the Institute staff to encourage you very strongly to fill in the questionnaires on the table. Fill them well. As statisticians, people are very anxious to have, well, perhaps not in this workshop, actually, have large N when they're assessing questionnaires. Have complicated missing values and all that sort of thing. So please take a few minutes to say whatever you wish on those questionnaires. So this morning we start with Inge Helland from Oslo to talk about PLS.
Thank you very much indeed. This is joint work with Solve CB, and what we are trying to do is to translate what is being done in another culture, the PLS culture or partial least square culture. And this is indeed a big culture, and it's not only confined to Scandinavia. There are Italian mathematicians working with PLS, there are Spanish and Portuguese mathematicians working with PLS, and there have been a number of international conferences devoted solely to PLS, and the next such conference will be held in China in a couple of years. So it's a big conference, it's a big culture. And it is something that rests on an algorithm. Now we are used to algorithms in this conference, but usually we have algorithms that are based on something else, some principle. And what I have tried to do some years ago is to go the other way, to take the algorithm at the point of departure and find something something like a principle behind it. But anyway, the algorithm itself is what we can say not optimal in any sense. It cannot be tied to any optimality principle, and it's also been proved by a different example, completely different from what I'm going to do, that it can be improved. The aims of this talk is to start with a parametric version of the PLS algorithm, argue that this is equivalent to a model reduction in multiple regression, and then discuss in application one can find an optimal prediction method by a better estimation of the parameters of the model, and then sketch an example at the end. Here is the algorithm in a way that I prefer to see it. We should not pay too much attention to the algorithm itself. It's connected to weights, scores, loadings, and new residuals. And then there's something more connected to the regression coefficient, taking in new observations. But why I want to point at one thing. The PLS algorithm, as it is introduced, is an algorithm for data. And then these covariances are estimated covariances. These variances are estimated variances. So this is my version where I try to look at the structure behind the thing, and I call this a parametric or population PLS algorithm. And in fact, there is a structure behind this thing, and to look at that in a simple way, we look at the covariance variance of the x's. We imagine that the x's are random and have some covariance matrix, and look at the spectral decomposition of that one, and then we formulate the regression coefficient in the shortest possible way using these principal components. This number of terms can be shortened in two ways. When you have coinciding eigenvalues, it's enough to take one eigenvector for these coinciding eigenvalues. And also when some of these d transpose sigma are 0, they can be deleted. So you can imagine that we have a sparsity here, not in betas, but in principal components. And this sparsity is connected to the PLS algorithm. These are old results from 20 years ago, but they are quite satisfying results in many ways, for they say that there is a way that this parametric PLS algorithm stops automatically, where W is 0, this W here. This is when WA plus 1 is 0, it means that the covariance between the residuals in the x and the y directions is 0. So there's no connection between x and y. So that is a natural way to stop the algorithm. And at that step, it turns out that the number A is equal to the number of relevant components M. That is the minimal number of terms here. And the beta PLS is equal to the beta that you get from this formula. So these are old results, but and they are concerned with the parameters, and the next step should be to estimate things. Maximum likelihood was tried, but it's not successful. The present approach is to do best equivariant estimate under some group. And it's known that this is equal to the base estimator under a right invariant prior of the group. So the one thing that I want to do is to choose the right group for this model reduction that corresponds to the model reduction that I have just sketched, and try to do that, to use that in estimation. So again, we have the random X multiple regression, we have the sigma, and the first group we try is rotation in the X space. That's a natural group to look at when the X variables have the same units, and a general requirement for model reduction is that the reduced model should be invariant with respect to a chosen group. This, I think, is a very useful criterion and very general criterion. I mean, one criterion for imposing a group to a model is that the whole parameter space should be invariant under the group. So the same thing should apply when you reduce the group in some way, delete some parameters. What you should end up with should also be invariant with respect to chosen group, and that may help in choosing the right reduction. So in general, we have linear combinations of gamma k, dk, and dk's are eigenvectors of sigma. And in this formula here, the ordering is of course arbitrary. And the transformation of rotation group is some way of finding the right group, but the result of that is that each order vector gamma 1 to gamma k corresponds to an invariant set. So we have too many invariant sets, and we can repair that by extending the group using a scale group in addition. In addition to rotation of the d's, we use a scale group for the gamma coefficients. And that is quite convenient. For the scale group has the property that it has two orbits, 0 and different from 0. These are orbits. And if you use that the whole group here for all the reductions here, then it turns out, and also use the thing that this is just the same if we order the gammas differently, then it's not the gammas that are equal to 0 that counts, it is a number of gammas that are equal to 0. So the invariant set in the beta space using this extended group, the rotation plus the scale group, is characterized by single m, the number of gammas which are non-zero. And that leads us really to PLS. So PLS can be characterized as the solution of the regression problem that is such that it is invariant under this combined group, the rotation of the gammas and the scale groups of this, the rotation of the these and the scale group of the gammas. So in a way, this is a precise link between the language of two cultures, and some of you remember the paper by Brayman with discussion, where you have a very nice discussion of two cultures in statistics. We have something similar here. We have two cultures in prediction, but the difference from Brayman's situation, where you looked at trees and so on, is that we can in fact translate from one culture to another and thus have a discussion between the cultures. So to estimation. In principle, we can now look at equivariant estimation in the reduced regression model. And a nice thing that is that, for instance, the ordinary PLS turns out to be equivariant. That is, the rotation estimated of beta is the estimated of the rotated beta. So if you can find the best equivariant estimated on this group, then this should be better than the ordinary PLS. And the best estimator is the base estimator, Pittman estimator, and you have to use an invariant measure which can be calculated as this. This is the invariant measure under the scale group of gammas and the rotation of the D. And that is what we have been trying to do. It is not quite easy to calculate this Bayesian estimator. We use MCMC, and it is a situation where the likelihood is quite complicated, but and our problem now is mainly that the MCMC solution turns out to be dependent upon where we start. So what we have here are some preliminary results, but it is a standard example from PLS thing, a situation where you have n equal to 50 and p equal to 100. You have a spectra, and the data looks like this, and the result we get is something like this. Here is the ordinary PLS, and this is the prediction error on a rather large test set, so it should be fairly accurate. And what we have done in calculating the base PLS is to use as a starting value a PLS with more components than we really need. Formal cross-validation first. And then it turns out that the algorithm deletes some of the components and ends up with a number of components equal to 8, which is the best according to the PLS. So the base, we initiate from 11 components, but we reduce to 8 components. And the base PLS perform marginally better than the 8-component PLS model for this data. And we have done the same with simulated data, and it's the same situation. We do better than PLS, but not much better. But the point is that the algorithm seems to iterate towards the best PLS solution. So the conclusion is that PLS can be improved by a model approach. And that's it.
Only 2 questions. Is there any comments?
I have one question. Why isn't, rather than doing the PLS, why can't you just find the top M principal components, empirical, I mean, given that the dimension is relatively small, and then since, of course, they're orthogonal to each other, just do regression in the simple way, just take
the difference between principal component regression and PLS is that in PLS you only specify the number of principal components. You don't specify which principal component that you have. So in principle, you have different versions of principal component regression according to order or whatever.
Thanks again.
Okay.